Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Houston, we don't have a problem. Today we're going to explore the notion of work. Now let me say something. It's really important, class, that you do the pre-video questions, because that's going to get your brain thinking about what we're going to talk about. So pause the video, do your pre-video question. Hey folks, today we want to talk about work. Work. Don't I do enough work? Probably so, but we're going to talk about work from a physics perspective. Physics and work. So what is work? Work has a very specific definition in the world of physics. If I have a block of wood or something like that, and I apply a force, I can push it or pull it. What happens often, if you can overcome the forces, is the object will move some distance delta d. So work is defined, write this down, when a force moves, it's important that it moves, an object, I'll just OBJ, in of the force applied. So it's important that as you apply the force, in this case in this direction, that it moves in this direction, right? If I apply a force, as a side note, if I apply a force in this direction and it doesn't move, you don't do any work. If there's no movement, there's no work. And so that leads us to like an equation. Work has an equation? Yeah, math. Super easy. Work equals the force applied, right? The force, what do you think? Times the distance. Now let's break that down into some units though. Now let's think about this again. So if we know that work is force times distance, and we know that force is mass times acceleration, we learned that in a previous unit, then we can say work is equal to ma, mad? I'm mad. You're mad. Work makes you mad. Mass, acceleration, and distance. But let's even break this down any further, okay? Mass is typically, right, in the SI system, is in kilograms. Acceleration, let's think that through, meters per second squared. Distance is meters. That's it. MAD is going to be a kilogram. It's kind of a crazy unit. Meter squared per second squared. All right? That's work. Now we simplify this and we actually give it a letter, and it's called a J, which stands for joule. We just use a joule. All right? So the joule is a unit of work. Also the unit of energy. We'll talk about that in a couple of videos. But that is how we solve for work. Now you might say, it's very important, like think this through. What if though, let's say that I have a big box and here I am, and it's a really big box, okay. And I apply some force. I push on it, and it doesn't move. Does it do any work? No. Unless the object moves in the direction of the force applied, there is no work. Let's do an example. And by the way, those of you who are not from my class and you're watching this on YouTube, what I would encourage you to do is you could go to houstonscience.org. Yeah, comment. By the way, if you're not one of my science students, there's notes, follow-along sheets, and you can just download those at houstonscience.com. But here, example. Well, here's the example. I've got it from the paper here that you students have, is that if I've got a wheelchair, right? All right, Mr. Bergman's not going to be able to drive a wheelchair. Okay, and someone's pushing the wheelchair, right? Nurse or somebody's pushing the wheelchair, right? And the patient weighs 68 kilograms. The wheelchair weighs 15 kilograms, that's the chair, okay? And it produces an acceleration of 0.60 meters per second squared. The question, and we push it for a distance of 3.5 meters. How much work does the pusher of the wheelchair, the nurse or whatever, have? So work is equal to force times distance. But now what do we know? This is a mass, this is a distance, and this is an acceleration. So we can also say this is equal to MAD. Now as a note, we need to add these together. So 68 and 15 comes out to 83 kilograms. So this is equal to 83 kilograms times the acceleration, 0.60, times the distance. We simply take our calculator, we multiply these three together, and we come up with 174. And I'm just going to simplify that and say joules, a kilogram, meter per second squared. This next section talks about how the angle makes a difference, right? So we've talked about just, pushing forces in the same direction. But imagine a guy, right? And he's pulling his suitcase through the airport. Now, of course, the force is going to be in this direction, right? But the object is moving in this direction, and this direction has an angle. Make sense? So what's going to happen is that the force is always, work happens in the direction of the movement. And as this person walks across the airport, this is actually, if you think about it, if I know this angle, this is the adjacent and this is the hypotenuse, it's actually going to be what? F cos theta is going to be your force, right? In your work is equal to force times distance, because this is adjacent, this is hypotenuse. And so you're going to have to plug this in here because it's only in the direction of the movement of the object. In this case, off to the right. So you could say, hey, if I know the distance and I know the force, I may apply a 15 Newton, but at 15 Newton times the cosine of whatever the angle is. So angle matters in these problems. So you're going to get some problems where you got weird angles. Got to figure out how to solve those. So let's do one of those problems, right? So from the paper here, we've got a situation where we've got a boat, all right? A lifeboat. So we got a ship. And then the ships, you may not know this, but the ships, they've got lifeboats and they're on ramps. And then they have to travel a certain number of distance. So according to this problem, we're going to suppose that this is a 5,000 kilogram lifeboat. It's a big heavy lifeboat, right? And it's at a 60-degree angle. The distance of the ramp is 5 meters. And so the question that we want to ask is how much work does gravity, because gravity is what's causing this to happen, right? This is, mg down here. How much work does gravity do in this problem when you release the boat? Well, again, we're going to do work is equal to force times distance. But now we have this angle thing right here. And we need to figure out what this is. We know this is 5,000. So this is equal to 5,000. And g, of course, is 9.8. So I got to find the force. So you take 5,000 times 9.8, you get 24,500. That'll be newtons. But this is the force downward, right? And so, but I need to use the one that's the cosine, right? The cosine of theta. So for the force, watch what I do. I'm going to say 24,500 cos of 60. That's the force, because that's the force that's going to move in this direction, times 5. And then you get your calculator out, and you get 122,500 joules. So that's how you solve problems. It's simple, cosine might be a sine depending on the trigonometry of the situation, and that's how you solve those problems. And then let me just end by just a couple of graphs. So work can either be positive, negative, or zero. So let's do like 3 cases. Case number 1, let's say that I have 2 forces right here. What kind of work? So I'm going to apply a force, a net force in this direction, but I got 2 different forces that are additive. So what am I going to have for this? Is this going to be positive or negative work or 0? Okay. So what you're going to have to do is they're going to say, well, we've got a force in this direction, boom. And then we've got a force in 2 directions. Right? So we've got a force from the second force vector, and I'm going to have to do some SOHCAHTOA stuff. And so ultimately, all we care about, though, is this part of that triangle. So really, it's going to be this plus this amount. And you're going to have to play, if I know this angle is 30 degrees or something like that, and I know what this is, you can play SOHCAHTOA games. And so this would be a positive force. Okay? Now here's an interesting one. You can also have one that would be like this. Okay, so we've got a positive force here, okay, in the x direction, and then we have a negative force, okay, that's going in the x and the y direction. But if the movement is only in the x direction, we're sort of making an assumption, then you would have this, if you will, plus this, and I'm making an assumption it's a little bit longer. And your net force is this, and guess what? If you have a negative force, then when you plug that into the equation, then you can have negative work, which indicates your work is going in the opposite direction. Make sense? And you could have them where they can all add up to 0, right? Actually, an interesting thing here is if we get a graph that looks like this and like this, the work is only going to be in the x direction, assuming that's the direction of movement. This may have no bearing. The y doesn't have any bearing on what's going to happen. But you can always have it so if they add up to 0, then you can have 0 work, because if it doesn't move, there's no work. All right, that's what work is. Work. Work with me, people, work! Houston, we got no problems. We'll see you in class.